Okay, today we're going to be looking at 4.1, which is an introduction to exponential functions. As a review from grade 10, we have the exponential laws on the right-hand side of your page, and we're going to apply these laws to solve some problems from grade 10. So a little review of terminology. The base of an exponent is the larger number, and the exponent itself is the small raised number. The whole thing is called a power. So 5 would be the exponent, 2 would be the base, and 2 to the power of 5 is the power. Now we can use what you've learned before to be able to answer problems and simplify exponential equations. To simplify a rational expression, including exponents, you can divide the coefficients. So we have 24 divided by -4, which is -6. And then for the exponents, you can just subtract the powers because of the quotient law. When you divide two powers, you can subtract their exponents. So 5 minus 4 is 1. P. -3 minus 2 is -5. And for Q, 4 minus -2 is +6. Now, if you have a negative exponent, what that means is that the exponent is on the wrong side of the fraction. So if you have a negative exponent on the top of a fraction, that means that that power should actually be on the bottom of the fraction. So here we have p to the -5. We don't have a fraction, so that means it's on top. So if we wanted to make that exponent positive, we could put it on the bottom of the fraction instead of, like it is now, on the top. Okay, so a negative exponent in the denominator is positive in the numerator, and vice versa. And that would be the simplest form with positive exponents. A similar thing here. When you have a power of a power, like these, we can simplify that by multiplying the powers together. That's the power law. That would be always a good first step. So -3 times 2 is -6. And 4 times 2 is 8. And now you can use the quotient law and subtract any powers, the exponents of any powers that have the same base. So 5 minus 8 is -3. And -6 minus -1 is -5. And this negative sign here just means that we're multiplying everything by -1. Okay, so the question asked me to write everything with positive exponents. So now I'm going to use the fact that anytime I have a negative exponent in the numerator, it can become a positive exponent by moving to the denominator. So I can put that a as a positive power of 3 in the denominator, and the same thing with the b. And that's just using the negative exponent law. Negative exponents become fractions, just like we saw in the warm-up. Now when you have a square root, we have a number of choices. We can try to simplify as much as possible inside of the square root. So unfortunately 49 and 16 are relatively prime. They don't go into each other. We can subtract the two exponents with the same base, the 7 and the 3. And we can use the negative exponent law to put the y, that's the power of -4, into the denominator to make it a positive. And now I could apply rule number 8. I can change this square root into 2 separate square roots. So a square root on the top and a square root on the bottom. The square root of 49 is 7. The square root of x4 is what times what would equal x to the power 4? X squared times x squared is x to the power 4. Okay, the square root of 16 is 4. And on the denominator, I clearly made a mistake. It should be y instead of x. Otherwise, everything would cancel off. Sorry about that. So your final answer is 7x squared over 4y squared. Are there any questions? Now the next section is where it becomes really useful for Math 12. So when it says convert to the base indicated, what that means is that we want to write 32 to the power of x as 2 to the power of something else. So let's take that 32 and write 32 as 2 to the power of something. So you can use your exponent grid to find out what is 2 as a power, or what is 32 as a power of 2. And it's 2 to the power of 5. 2 times 2 times 2 times 2 times 2 is 32. And now I can use the power law to combine those two exponents. Multiplying 5 and x, I get 2 to the power of 5x. Okay, so 32 to the power of x is the same as 2 to the power of 5x. I can do the same thing for 81. Okay, because 81 is a power of 3, so I can change the 81 into some power of 3. So I'm going to write that as 3 to the power of 4. And again, I can use my power law to combine the two exponents. I just have to make sure that I have brackets around the second exponent, because that 4 is going to multiply to everything. Okay, so this is the same as 3 to the 4x minus 2. And if I expand, that's the same as 3 to the 4x minus 8. Same thing goes here. I can take the 1 over 64 and I can write this as 1 over 64 to the power of 2x. Because if I have 1 to the power of 2x, it's still 1. So now I'm going to take this 1 over 64 and I'm going to write that as some power of 4. So looking on my exponent table, I can see that's 4 to the power of -3. Okay, negative exponents give fractions. Now combining the two exponents through multiplication, -3 times 2x is -6x. And this can help you simplify really complicated expressions. So any idea what we might use as a common base for an expression like question 3? (9, 27, 81), they all fit really nicely on the row of powers of 3. So let's use 3 as our common base. So instead of 9, I'm going to write 3 squared. Instead of 27, that's 3 times 3 times 3. And instead of 81, I'll put 3 to the power 4. Now you can use the power law to combine all your exponents through multiplication. Don't forget that you actually have to expand it into the brackets. So 2 times 2x, 2 times 3. 3 times 3x is 9x. 3 times negative 1 is negative 3. 4 times x is 4x. And 4 times negative 1 is negative 4. And then now I'll use the basic laws from above. The fact that if you multiply 2 powers, you can add their exponents. And if you divide 2 powers, you can subtract their exponents. And just a note, this is actually the same as x to the n divided by x to the m. So writing it as a fraction or division means the same thing. So now what I can do is I can take the common base of 3, and I can just take my 2 exponents that are being divided, and I can subtract those ones using one common base. And I can take my exponents that are being multiplied, the powers that are multiplied, and I can add their exponents. And that turns the expression into a much, much simpler expression with one base. So I could put that negative sign into the second bracket. You can write this below. I won't actually be doing question number 4 with you. So we've got 4x plus 6 minus 9x plus 3 plus 4x minus 4. And now combining like terms, 4 plus 4 minus 9 is negative 1x. 6 plus 3 minus 4 is plus 5. So 3 to the negative x plus 5 is the same as 9 to the power of 2x plus 3 divided by 27 to the power of 3x minus 1 times 81 to the power of x minus 1. So you might be wondering, what's the point? So instead of question number 4, we'll just do one example where you can see how this can help us to solve complicated equations. So you might have something like 9 to the power of 2x minus 3 equals 27 to the power of 1 minus x. Okay, so you can write this down instead of question number 4. Sometimes you're going to see questions like this where you don't have a common base. But here you can see that both of them are powers of 3. So instead of writing 9, you can write 3 squared. And instead of writing 27, you can write 3 cubed. And following the same steps as you did above, we're going to expand the exponents through multiplication. And now we'll use the principle, if the bases are the same, if you have one base on each side and the base is the same, then the exponents must be the same. The only way that you can get 3 to the power of something to equal 3 to the power of something is if it's something like 3 to the power of 2 and 3 to the power of 2. Both the exponents have to be the same. So 4x minus 6 equals 3 minus 3x, because the bases are the same. And now you can solve this just like you would any equation. Add 3x to both sides. And add 6 to both sides. And divide both sides by 7. So x is 9 over 7. Any ideas about how you could check that answer? Plug it in. And my favorite one? To solve any equation in math? Graph it. Graph both sides. All you have to be careful about when you're graphing is that you do put brackets around a complicated exponent like this one. So you'd graph the original equation as both two different y equations, and you'd be able to see that it crosses at 9 over 7. Yes, question? So you can look at the video to find the rest. So here's a basic shape of an exponential function on the back side. It starts off really slow. It has an asymptote on the x-axis. The basic graph crosses the y-axis at 1. And it goes through the point 1, 2 to the power of 1, because this is the graph of 2 to the power of x. And it goes through the point 2, 2 to the power of 2. And it goes up really quickly. So it starts off really slow and then it gets super steep. So after 1 foot, the height would be over 100 yards. After 2 feet, we're talking about 264 miles. After 3.5 feet, here, the height of it is going to be at the sun. And if I lay down and found my height across, the height of this graph would be 1 light year up. Okay, it's enormous. A basic exponential function can be written in the form y equals a b to the power of x. And b is the base. And a would give it a vertical extension. Okay, and your base always has to be positive. Okay, so I hope that last year you learned about compound interest. That when you invest a starting amount at a certain interest rate for a certain number of years, then A is your total amount. Now this equation only works if you're compounding annually. So I'm going to make this a little bit more difficult, and let's change this question to compounding monthly. Did you learn about this last year? Grade 8. Okay. This equation will be given to you on a test. You don't need to memorize this one. I'll give it to you. There's a slight modification if you compound, and you can write that on the side. If you're compounding it monthly, then you're going to take your interest rate and you're going to divide by the number of times that you compound. And then the power is going to be multiplied by the number of times that you compound. So compounding just means that the bank pays you interest like every month. So if I put in $10,000 at 9%, then 9% would be fantastic. I'm lucky if I can get 2%. Then I would get $900 the first month. Not the first month. Over the first year. Okay? That 9% represents a whole year. But if they compound it monthly, that means that they're spreading the 9% out over the year. That they're giving me 0.75% every month. So they're paying me a little bit of interest every month. And that way, instead of getting $900 for the year, I'm going to get a little bit more than $900 for the year. We'll find out how much more. So if you wanted to write this as an equation, you would say that the total amount that you get is the starting amount times 1 plus the annual interest divided by the number of times you compound to the power of the number of years times the number of times you compound, which in this case, we're starting with $10,000. The interest rate is 9%. I write it as a decimal, 0.09. And the number of times that I compound is 12, because it's monthly. And then I would leave n as a variable, because it doesn't tell me in this equation how many years. So if I just do a simple calculation and find out how much money would that be for 1 year. So I add 1. Adding 1 means that it's growing in interest. And now I do that to the power of 12, and times by the original. So instead of getting $900 of interest, I get $938. Because they gave me a little bit of interest every month, and I got interest on that interest. So that's what compounding does. It gets me a little bit more money. I know it's not that much, but after like 10 years, it would make a huge difference. How much difference? That's a great question. So we can find out what happens after 10 years by graphing it on the calculator. And we can find out how much time does it take for the investment to become $20,000. So in order to do this, we can graph the function 10,000, 1 plus 0.09 over 12. And make sure you always have brackets around your exponent. And then as our second equation, we can graph y2 is 20,000, and we can see when those two equations cross. So you can pull out your graphing calculators. There he is. So you can put x instead of n. 1 plus 0.09 over 12. And make sure you got brackets around the exponent, 12x. Because this is exponential, it's going to get really large. We're talking about lots of money here. So my window, I want to go from 0 years to 10 years. And my y is going to go from $0 to probably $20,000 at least. Let's see what that looks like. Yeah, I need to go a little bit higher maybe to see it all. Maybe I'll go up to 30,000. So you can see when it's 0, I start with $10,000. And over 10 years, it starts to go up gradually. So here I'm going from 0 to 10 years, and I'm going from $0 to $30,000. Oops, not very straight. and this point here is my y-intercept. So now I want to find out how long does it take to get to a height of 20,000. I want to see where those two lines cross. So I'm going to plug in 20,000 and see how many years it takes for it to double. So let's calculate the intersection, number 5. Enter, enter, enter. And it intersects when x is 7.73. So it takes almost 8 years. That's really amazing. Good luck finding 9%. Usually we're going to round up to the nearest year. You don't have to break it down to how many months. Are there any questions? Okay, so your practice for today is page 159, numbers 1, 2, and 9 CE.